Welcome, curious minds, to a whirlwind tour of the universe's most enigmatic beasts, black hole singularities. In just a few minutes, we'll shatter every myth you thought you knew. First up, imagine matter crammed into a point of infinite density. It's not just heavy, it's infinitely heavy, a cosmic singularity that bends the very fabric of reality. Next, the event horizon, think of it as an invisible one-way door. From the outside, time freezes as anything crosses, yet the traveler feels only a heartbeat before doom. Feel that stretch? That's spaghettification, where tidal forces pull you apart like pasta, a fate no astronaut ever wanted. But what about the information that falls in? Quantum mechanics insists data can't vanish, yet black holes seem to purge it, igniting the infamous firewall paradox that keeps theorists up at night. Meanwhile, Einstein's famed equation, E=mc², gets a cosmic makeover. A black hole's mass mirrors the colossal energy birthed in its collapse, linking the tiniest particles to the largest structures. And when two black holes tango, they send ripples, gravitational waves, through spacetime. Scientists hunt for faint echoes within those waves, hoping to glimpse the singularity's hidden architecture. Even singularities aren't entirely silent. Stephen Hawking showed they leak a ghostly glow called Hawking radiation, a whisper that, over eons, can evaporate a black hole entirely. This tiny emission turns these titans into fading embers, a reminder that even the fiercest forces age. Yet these mysteries push us to the frontier of quantum gravity, where our best theories clash and scramble for answers. The singularity's size? 0. No radius, no volume, just a point where density becomes meaningless. Finally, the cosmic censorship hypothesis argues nature hides these infinities behind event horizons, shielding the universe from raw, unforgiving chaos. So far, we've only brushed the surface. Each fact is a doorway to deeper questions, each paradox a signpost toward the next breakthrough. Stay tuned, because the adventure has only just begun. But that's just the beginning. In Part 2, we go deeper. Welcome to Part 2 of our deep dive into one of the most enigmatic objects in the cosmos, the black hole singularity. In the previous episode, we laid the groundwork, defining event horizons, Schwarzschild radii, and basic relativistic concepts. Today we travel back to the early 20th century, when Albert Einstein's general theory of relativity opened a portal to a new kind of astrophysical object. In 1915, Einstein presented field equations that described how mass and energy warp spacetime. That same year, Carl Schwarzschild solved these equations for a spherically symmetric mass, uncovering a radius at which the escape velocity equals the speed of light, a boundary that would later become known as the event horizon. The idea of a point of infinite density, however, lingered in theoretical shadows for decades. Fast forward to the early 1960s, when Roy Kerr extended Schwarzschild's solution to rotating bodies, showing that black holes could spin at nearly the speed of light. This discovery paved the way for Roger Penrose's singularity theorem in 1965, a rigorous proof that under realistic conditions such as the collapse of a massive star, a singularity must form. Penrose's work was a watershed moment. It transformed black holes from mathematical curiosities into inevitable outcomes of stellar evolution. By the late 1970s, Stephen Hawking added quantum mechanics to the mix, proposing that black holes emit radiation, now famously called Hawking radiation. This quantum leakage hinted that the singularity is not a dead end, but a doorway to new physics. Understanding the physics of singularities requires mastering both general relativity and quantum theory. General relativity tells us that spacetime curvature intensifies as mass compresses, eventually diverging toward infinity at the singularity. The Schwarzschild radius, derived in 1916, defines the sphere where this divergence becomes observationally hidden. Inside that sphere, traditional notions of distance and time break down. In 1971, Hawking demonstrated that quantum fields in curved spacetime produce particle-antiparticle pairs near the horizon, an effect that causes black holes to lose mass over astronomical timescales. This interplay between gravitation and quantum fluctuations suggests that singularities are the ultimate testing ground for any theory aspiring to unify the two realms. But how does a singularity actually form? The classic Oppenheimer-Snyder model of 1939 provides a clear picture. When a massive star exhausts its nuclear fuel, the outward pressure that once balanced gravity collapses. The core contracts, and if its mass exceeds the Tolman-Oppenheimer-Volkoff limit, about 3 solar masses, the collapse proceeds unchecked. As the core shrinks past its Schwarzschild radius, an event horizon forms, cloaking the singularity from the outside universe. Numerical simulations in the 1990s revealed that tidal forces near the horizon stretch infalling matter into long filaments, a process poetically described as spaghettification. By the time matter reaches the central point, all known physical laws cease to be predictive, the density and curvature become mathematically infinite. Leading scientists continue to wrestle with these extremes. Kip Thorne, who helped design the narrative for Interstellar, describes singularities as the edge of physics, where our current equations become insufficient. Penrose, meanwhile, has advocated for the idea that information is not destroyed, fueling the ongoing firewall debate. The Event Horizon Telescope's landmark image of the supermassive black hole in galaxy M87, released in 2019, offered the first visual confirmation of an event horizon, though it cannot directly image the singularity itself. In 2022, a collaboration of LIGO and theoretical physicists published simulations suggesting that quantum gravitational effects could imprint subtle signatures on gravitational waves emitted during black hole mergers, hinting at the singularity's influence. Why does any of this matter beyond academic curiosity? Singularities sit at the crossroads of the two pillars of modern physics. The information paradox, first articulated by Hawking in 1976, challenges our understanding of entropy, causality, and the very notion of determinism. Resolving how information behaves at a singularity could unlock a coherent theory of quantum gravity, potentially revealing new particles, forces, or even pathways to harnessing extreme energy. Moreover, the singularity problem informs cosmology. The Big Bang itself can be modeled as a singularity, and insights from black hole cores may illuminate the universe's earliest moments. In short, the singularity is both a profound mystery and a beacon guiding the next generation of theoretical breakthroughs. As we conclude Part 2, remember that each layer of understanding we add brings us closer to reconciling the elegant curvature of Einstein's spacetime with the jittery world of quantum fields. Our journey through history, core physics, formation mechanisms, expert commentary, and broader significance has set the stage for the next episode, where we will peel back the observational veil and explore the phenomena that mainstream sources often gloss over. In Part 3, we uncover what mainstream sources won't tell you. It starts with a question that haunts every astrophysicist: what really sits at the heart of a black hole? The answer is hidden behind layers of theory, data, and mystery, and today we peel them back one by one. First, imagine a region where light itself cannot escape, an abyss that devours everything, even time. For years we thought this singular point was a cosmic dead end, a place where our equations simply break down. But cutting-edge research hints at something more exotic, a bridge to a hidden realm where the fabric of spacetime folds in on itself, creating pathways we have yet to map. This revelation forces us to rethink the very notion of a point in the universe. Moving deeper, Einstein's relativity gives us a picture of infinite density, a crushing singularity. Yet quantum mechanics whispers a different story, one of frothy, restless energy bubbling at the brink. If those quantum fluctuations dominate, the singularity becomes a cauldron of creation, not a void, where new particles might be born from the chaos. This paradox sits at the crossroads of the biggest theories we have, and it could rewrite the rules of physics. Picture now a coordinate where 3 dimensions collapse into a single, unknowable value, where space and time dissolve into nothingness. That sounds like pure science fiction, but the mathematics of black holes describes exactly that. Distances shrink to zero, yet the mass remains staggeringly large, a paradox that challenges our intuition about the universe's structure. This is the heart of the mystery, the point where our understanding reaches its limits. At that boundary, quantum fields jitter wildly, producing particles that flicker in and out of existence like fireflies in the dark. Some scientists propose a firewall that incinerates anything that dares cross the event horizon, while others argue that information is not destroyed but instead radiates away in subtle, almost undetectable forms. The debate is fierce, and each side offers a glimpse into a possible truth about how the universe safeguards its secrets. If we finally accept that the singularity can store information, then it acts as a cosmic ledger, preserving a record of everything that ever fell into it. This hidden blueprint could be the key to unlocking the deepest secrets of the cosmos, linking the mysterious interiors of black holes to the very fabric of reality. As we stitch together these pieces, relativity, quantum mechanics, and the notion of information, we see a picture that is both terrifying and awe-inspiring. The singularity is no longer just a mathematical oddity, it is a dynamic, information-rich arena that may one day reveal how the universe works at its most fundamental level. The journey from mystery to revelation is far from over, but each step brings us closer to the truth. Stay with us as we dive ever deeper, because what comes next will change everything you thought you knew about black holes. Now that you know the truth, Part 4 will change how you see this forever. Welcome back to the final installment of our deep dive series on black hole singularities. In this masterclass, we will weave together a century-long narrative, starting with Carl Schwarzschild's pioneering 1916 solution that mathematically described a point of infinite density. That insight, paired with Oppenheimer and Snyder's 1939 collapse model, laid the groundwork for the modern black hole concept, while Roger Penrose's singularity theorems of the 1960s proved that under Einstein's equations such a breakdown is not a mere curiosity but an inevitable feature of spacetime. From there, we transition into the heart of general relativity, the Schwarzschild radius, the event horizon, and the divergence of curvature scalars at the singular core. These equations reveal that classical physics reaches a hard wall where the metric tensor ceases to be defined, signaling that a new framework is required. Quantum mechanics steps onto the stage with Hawking's 1974 revelation that black holes are not completely black, they emit a faint thermal spectrum of particles. This Hawking radiation ties thermodynamics, quantum field theory, and curvature together, yet it also deepens the mystery of what happens to matter inside the horizon. Contemporary approaches, loop quantum gravity and string theory, replace the traditional point singularity with a finite, quantum fuzzy region, effectively smoothing out the infinite density while preserving the black hole's mass and angular momentum. These ideas are still under development, but they offer a glimpse into a quantum-corrected description of gravity. Observational evidence now grounds our theoretical speculations. The landmark detection of gravitational waves by LIGO in 2015 provided a new probe of black hole mergers, allowing us to infer the final object's mass, spin, and even indirect information about its singular core. In 2019, the Event Horizon Telescope captured the silhouette of M87*, confirming the predicted photon ring and lending visual confirmation to Einstein's equations near the event horizon. Meanwhile, supercomputers simulate the nonlinear dynamics of spacetime at unprecedented resolution, generating detailed models of how horizons fluctuate and how information may be encoded on their surfaces. The community remains sharply divided over the information paradox, a puzzle that asks whether information that falls into a black hole is irrevocably lost, violating quantum unitarity. Some physicists champion the holographic principle, suggesting that all the data is stored on the two-dimensional horizon, while others defend the firewall hypothesis, which posits a lethal wall of high-energy particles at the horizon. Recent proposals of soft hair, subtle quantum charges that decorate the horizon, attempt to reconcile the need for information preservation with the smooth geometry demanded by relativity. These debates are not merely academic, they shape the direction of research in quantum gravity and influence how we interpret the ultimate fate of matter and energy. Looking forward, the next generation of detectors, such as the Einstein telescope and space-based interferometers, will push sensitivity deeper, potentially capturing high-frequency gravitational waves from the final plunge of matter into the singularity. Coupled with advanced X-ray observatories, these instruments could detect emissions from the innermost stable circular orbit, offering clues about the quantum structure at the edge of the horizon. Artificial intelligence is already accelerating numerical relativity, enabling us to resolve horizon microfeatures that were previously computationally prohibitive. By refining our models, we inch closer to a unified picture where the singularity is no longer an inscrutable point but a well-understood quantum object. Why does this matter? Beyond satisfying curiosity, singularities sit at the crossroads of the fundamental forces. Understanding them could unlock a theory of everything, resolve contradictions between quantum mechanics and general relativity, and illuminate the destiny of information in our universe. Moreover, the philosophical implications reshaped by singularities challenge our notions of reality, causality, and the limits of observability. As we stand on the brink of new discoveries, the singularity remains a beacon of the unknown, urging us to push the boundaries of knowledge. If this series gave you value, subscribe. More deep dives coming every week.